So let's have a look at some of the examples of differentiating from first principles. Now, also this section allow me to divide it into two other parts, and how we are going to have differentiation of functions from first principles, but then the first set of functions is going to be polynomial functions, and then the other set is going to be trigonometric functions. So you're going to have differentiation of polynomials from first principles, and then later on we shall have differentiation of trigonometric functions from first principles. So let's begin with polynomials. Then let's take an example of, in the first section we had a look at differentiation of explicit functions, and then in that case we are using power rule. Then we had an example like of y equal to x squared, something like that. And then we said by using power rule, we found the derivative dy dx being equal to 2x. And then so in this case, we want to prove that, or to show that even when we use differentiation from first principles, it will give us the same answer as dy dx equal to 2x. Right, so let's begin. We know that, and then in this case, our y equal to fx, it is going to be this very first equation here, that y equal to x squared. It is going to be like our function of y equal to fx. And then so let's begin by adding small changes in both in y and in x. And then a point to note here is that when we add, for example, y plus change in y, it is equal to, in this case here, it is not x squared plus change in x. It is x plus change in x. Then that's when we square. So happen to note that the change in x, we only add it on x. You take note of that it is not x squared plus change in x, but it is x plus change in x squared. Then so this was our first step, and then after that we had step number 2 as subtracting the two equations, whereby you have our first equation as y equal to x squared. Then we also have y plus change in y equal to x plus change in x squared. So let's subtract the two equations, and then we had that you subtract y equal to x squared, which is in the form of y equal to fx, from this second established function. This is what we are going to be having. It's like saying that y, like having here y plus change in y, then minus y equal to x plus change in x squared minus x squared. So by so doing, you happen to find that we've subtracted this equation from this other equation which we've established in the first step. And then so what is this going to resolve to? We shall remain with this y and this y here, they will cancel. So we shall remain with change in y equal to x plus change in x squared minus x squared, like that. And then so what's next after doing that? Then here, in most cases, you'll have to first simplify the expression we will have gotten. So how will we simplify this expression? We have change in y. Equal to. So what we are going to do in this case, it is that we are going to simplify this bracket, or to square this bracket. And then this is going to give us, so it's like having x plus change in x being multiplied by x plus change in x minus x squared. So you happen to note that we are trying to multiply this other bracket, the bracket of x plus change in x, by itself, because it was being squared. And so let's open the brackets. We shall have change in y equal to this x with this. We shall have x squared plus this x with a change in x change in x, plus still change in x times x, it will give us x change in x, then plus change in x times change in x will give us change in x This one here, it will give us change in x by this change in x squared, and then this will be, close that bracket, then minus x squared. So what's next here? Let's try to simplify this expression. We shall have change in y. Equal to x squared plus this x change in x plus x change in x. It will give us 2x change in x plus the change in x squared, then minus x squared. So I happen to find that, or to see that this minus x squared with this positive x squared, they will cancel out, and then we shall remain with change in y equal to x change in x plus change in x squared. Now here you can get to the next step of dividing through by change in x, and then there we shall have, so in this case here we shall have change in y out of change in x, then even the other side we divide through by change in x, and it is going to give us 2x change in x plus change in x squared divided through by change in x. And then last, and then this can be further simplified to, remember this is 2x change in x plus change in x squared being divided by change in x. So here you happen to note that we can have, it's going to give us change in x, it will divide 2x change in x, and then we shall only remain with 2x, and then it will also divide the change in x squared, and we remain with only change in x. So this is going to give us 2x plus change in x. And then so here we can get to the last step of finding the derivative function, whereby we take the limit of dy dx, or I mean the limit of change in y over change in x, and that will be the dy dx. So our derivative function, that is dy dx, it is equal to the limit as the change in x approaches 0 or gets close to 0 of change in y out of change in x. And then we are going to substitute change in y over change in x with this expression here, because it is the expression for change in y over change in x. So it is going to give us, dy dx is going to give us the limit as change in x approaches 0 of 2x plus change in x. And then as the change in x approaches 0, or as it gets closer and closer to 0, we shall only remain with 2x. And then this is the same as the first expression we got, the derivative expression we got in the first section when we are using power rule. This one here, this expression here, that dy dx equal to 2x. So then you happen to find that we are getting the same expression even when we've differentiated the function y equal to x squared from first principles. And that this is a derivative function, or the gradient function of the slope y equal to x squared.